In this second lesson on statistics using Microsoft Excel, I'm going to look at the student t-distribution. When many replicate analyses are performed, the normal distribution is used to interpret and report results. But when less than 30 replicate analyses are performed, we use the student's t-distribution. This was developed in the early 1900s by William Gossett. So here the upper curve with infinite degrees of freedom represents the normal distribution, and 95% of the area falls within plus or minus 1.96 standard deviations from the mean. The middle curve, colored blue, represents a distribution with 6 degrees of freedom, or 7 samples. And with 3 degrees of freedom, we have this red curve. So notice that as the number of degrees of freedom decreases, these curves spread, and as the number of degrees of freedom increases, these t-distributions eventually become the normal distribution. So confidence interval and confidence limits. We get confidence interval and confidence limits using the student's t-distribution. The standard deviation of a set of data is a good measure of the precision in a procedure or analysis, but by itself it does not indicate how close the experimentally determined sample mean, x bar, is to the population mean. Did you appreciate that? When you calculate a sample mean, it doesn't necessarily tell you where the population mean is. The numeric range within which the population mean falls within a certain probability is called the confidence interval. Confidence limits are the upper and lower bounds of the confidence interval. So the confidence limits of the population mean are given by x bar plus or minus t times s over root of n. S is the standard deviation of the sample, t is the t-factor, n is the number of observations. And this term, t times s over root of n, is referred to as the margin of error. So where do we get these t values from? Well, there's tables of student t-factors, which are a function of degrees of freedom, here in the leftmost column, and the probability along the top. For example, with 1 degree of freedom, and that represents 2 samples, at the 95% confidence level, the t-value is 12.7. Now that's brutally high. You'd have to multiply that by your standard deviation when calculating the confidence interval within which the population mean lies. However, if you take one more sample, so 3 samples, 2 degrees of freedom, your t-value drops by a factor of about almost 3 times. So that greatly narrows the confidence interval. More samples, the better. With 4 samples and 3 degrees of freedom, our t-value drops to 3.2. With 5 samples and 4 degrees of freedom, 2.8, and so on. There's a decreasing return. You can see that as the number of degrees of freedom keeps increasing, eventually the t-value becomes the z-value for 95% confidence level. Remember, 1.96 standard deviations from the mean includes 95% of the values under the normal curve. Here's what it looks like. After we calculate the margin of error using a t-value, we can say that the true population mean falls somewhere within this range 95% of the time, and that leaves 5% probability that the true population mean could be outside the range, 2.5% either side. So there's an example of the calculation of confidence interval and confidence limits in our Excel spreadsheet. Let's take a look at that. So this Excel file is called Excel Stats. We're working on the worksheet called Confidence Limits. Take a look at this example. A sodium carbonate sample is analyzed in the lab by titration with standard HCl. The analysis is performed in triplicate with the following results: 93.5, 93.6, 93.4% sodium carbonate. Within what range are you 95% confident that the true value lies? That is the population mean, not the sample mean. I have the data here in column D. Let's work down this column. I will explain later why we're calculating some of these particular values. So we want the mean. That's simply the average function equals AVER. Tab to select, scroll over the arguments and enter 93.50 as the average. We'll come back to the standard error when we get other data. Let's get the median equals MED tab. So the median is simply the middle value. The standard deviation of the sample equals STDEV. It's .S tab. S is for sample. Scroll over the arguments, enter 0.075. Now the variance is just the standard deviation squared. We could do that, but there is a function for it, so let's use that. Equals VAR, again .S, not P. We don't want the population variance, but sample variance, tab. The variance is 0056. All right, let's get the min and the max equals MIN, tab. Now you say, Barry, I could just pick those out. Well, you're right, but once you have a spreadsheet set up, you can put your data in, and all the values are automatically generated each time. Equals max, tab. All right, now we can get the max minus the min. That'll be equal to cell D26 minus cell D25. That's 0.15. The count is simply the number of samples, equals COUNT, tab, and select. So as we suspected, there's 3 samples. We can get the standard error. It's simply the standard deviation divided by the square root of the number of samples. That'll be equal to cell D22 divided by SQRT, tab. Number of samples here is the count. That's 3. D27. 043 is a standard error. So the standard error is, of course, less than the standard deviation because you divide by the square root of the number of samples. Now the confidence level that we're testing at is the 95%. It's not a function, it's just information for us. Now to do the calculation we need, if you look here, t times the standard deviation over root of n, or t times the standard error, which we got up here. We need a t value. We could look in a t table. Here are the number of observations. That would be 3. The number of degrees of freedom is 2. At the 95% confidence level, it's 4.3. We could read it. We could use a lookup function, but there is a function in Excel for t values. It's this here, equals t.inv.2t for two-tailed. We'll talk more about this later. And then the alpha value, that is the probability, and degrees of freedom. So here equals t.inv. There it is, 2t. Scroll down, tab. The probability is 95%, but it's given as what is called an alpha value. So our alpha value will be 0.05. That is 100% minus 95%, written as decimals, is 0.5. And that's often how probability is reported. So an alpha value of 0.05 corresponds to our probability level of 95%. Comma, degrees of freedom is n minus 1, so that would be 2, close bracket, and we're told it's 4.3, and notice that does agree with the t-table value. Now to get our margin of error, it's simply t times s over root of n, or t times the standard error right up here, and we'll just do that. That'll be equal to the t value in cell D29 times the standard error in cell D20, enter. So it's 0.186. And that's the amount that we add and subtract to our sample mean to give us the confidence limits. So the lower confidence limit will be the mean, the sample mean, minus the margin of error. That'll be equal to our average cell D19 minus our margin of error, which is now hiding. Let's see what's that in cell D30. D30 30, enter, 93.32, and the upper confidence limit is the mean plus the margin of error equals the average plus our margin of error, enter, 93.69. So what we're saying here is this. We are 95% confident that the true population mean lies within the confidence interval between 93.32 and 93.69. At the 95% confidence level, we are confident that if this analysis were performed 100 times, then 95 times out of 100, the population mean would fall within our confidence interval, that is the range between the upper and lower confidence limits, and that's surrounding our calculated sample mean. So it's a fairly straightforward calculation, and it's very important and useful. Now Excel has a function that calculates this margin of error directly, and here's the syntax, equals confidence.t, and the arguments are alpha, the probability, 0.05 in our case, the standard deviation, and the number of samples. Let's give it a try. Equals confidence t, there it is, scroll down, tab, alpha, 0.05, comma, the standard deviation, we calculated that up here. Cell D22, it's 0.075, comma, and the number of samples is simply our count value of 3. Close the bracket, and there's 0.186. An easy calculation to perform in Excel. Page 178. We really need to spend just a couple of minutes so we get a good understanding of the difference between the standard error of the mean and the standard deviation of the sample. So please follow with me. Assuming random variation, that is a normal distribution of replicate measurements, the following formulas are applied. If we have a large number of replicate samples, n greater than 30, then the standard deviation or standard error of the sample, Sd, S sub x, Se, stats has so many acronyms, synonyms for the same thing, that would be approximately equal to the standard deviation of the entire population, which we call sigma. So we can say in this case the standard deviation of the sample is approximately the same as the standard deviation of the population, which is equal to the root of the sum of the squares of the differences between samples and the mean divided by n, the number of samples. So when sigma is known, or n is large, greater than 30, we use the z-stat. And the margin of error is equal to plus or minus z times sigma over root of n. So x bar plus or minus z times sigma over root of n defines the confidence limits within which the population mean will lie at some confidence level. Sigma over root of n is called the standard error of the population mean, SEM, it's often abbreviated as. It's the standard deviation of the population mean. At the 68% confidence level, z is equal to 1. And so x bar plus or minus sigma over root of n defines the 68% confidence limits within which mu will lie. But at the 95% confidence limits, z is equal to 1.96, so x bar plus or minus 1.96 times sigma over root of n defines the 95% confidence limits within which mu will lie. Now what happens when you have a small number of replicate samples, n less than 30? Then the sample standard deviation, Sd, S sub x, or Se, is calculated as the root of the sum of the squares of the differences between the individual and the mean divided by n minus 1. So when sigma is unknown and n is small, less than 30, the t-stat is used and the margin of error becomes plus or minus t times sx over root of n. So x bar plus or minus t sx over root of n defines the confidence limits within which the population mean will lie. And so Sx over root of n is also called the standard error of the sample mean, SEM, the standard deviation of x bar. at 68% confidence level, t is equal to 1, just like z was equal to 1 at the 68% confidence level. And so x bar plus or minus sx over root of n defines the 68% confidence limits within which the true population mean will lie. At the 95% confidence limit, x bar plus or minus t times sx over root of n defines the 95% confidence limit. But the t value depends, of course, upon the confidence level and the degrees of freedom, n minus 1. Please stay with me here. This is important to understand. So the standard deviation, S, versus the standard error of the mean, SEM. When the same sample is repeatedly analyzed, the standard deviation of the results defines the range within which the sample is likely to fall 68 times out of 100. And if you visualize this, you will appreciate that the average of replicate sample analysis, that is the mean, will also fall within a range. But the range should be narrower than the range of the standard deviation of individual samples. Now, why is that? Well, because the mean resides at the middle of individuals' results, not at the extremities, otherwise it would not be the mean. So looking at the formula for the margin of error, t times s over root of n, or z times sigma over root of n, it would appear that the margin of error should be less than the standard deviation, or less than sigma, because you're dividing by root of n. But the opposite is true when n is small. The graph on the following page shows that margin of error is greater than standard deviation when the degrees of freedom are less than 5, or margin of error is greater than sigma when degrees of freedom are less than 3. What's going on? Well, let's take a look at the graph and we'll come back. So here, let's deal with this black line here. This is simply the t values as a function of degrees of freedom. So notice that with 1 degree of freedom, or 2 samples, the t value is 12.7. Ouch, that's huge. When you go to 2 degrees of freedom, or 3 samples, the t value drops to 4.3. With 3 degrees of freedom, or 4 samples, it's down to 3.2. 4 degrees of freedom, which is 5 samples, 2.78. It's a decreasing return. Now look at the blue line here. This is the margin of error calculation. Now assume that standard deviation is 1, right? At what point does the margin of error become less than 1? The formula is t times s over root of n. Well, if you only have 1 degree of freedom, or 2 samples, your margin of error is actually 9 compared to a standard deviation of 1. That's huge. And with 2 degrees of freedom, or 3 samples, now the margin of error drops to about 2.5, but it's still much greater than the standard deviation of 1. Here's the point with 3 degrees of freedom, or 4 samples. Now a margin of error is 1.7-ish or something like that. Notice at what point does the margin of error actually come down and equal 1? Well, something more than 5 degrees of freedom. I have it in a chart up here, actually calculated. So here is the margin of error, assuming standard deviation of 1. The margin of error will actually finally come down to about 1 when we have 6 samples, or 5 degrees of freedom. It's only when you have more than 5 degrees of freedom, or more than 6 samples, that your margin of error actually gets smaller than the sample standard deviation. Now when we use the z-stat instead of the t-stat, z times sigma over root of n, assuming again that sigma is 1. It's only when the number of samples reaches 4 or more, the degrees of freedom reaches 3 or more, that the margin of error actually is smaller than the population standard deviation. Back to page 178. So just so you don't miss it, what's going on here? You must appreciate that although unlikely, it is entirely possible that in a small set of samples, all the x values could fall right near the extremities of the sample distribution. In such a case, the sample mean x bar could be quite far from the population mean, and hence, for small data sets, the t value is really large. And it's only when the degrees of freedom is greater than 5, when using a t value, or degrees of freedom greater than 3 when using a z-value, is the margin of error finally less than the calculated S, either standard deviation or sigma. So when you need to report margin of error along with a mean, and you always must, it is important to perform a good number of replicates so that you can report a small margin of error, and we all want to. I can't report to my boss that the chloride concentration is 17 plus or minus 5. My boss is going to send me home. I have to be able to say 17 plus or minus 1, or 17.1 plus or minus 0.1. And in order to do that, I need one or both of two things. I need more replicates, and I need really high precision on the samples that I do take. And of course that means more work, but that's what I get paid for, right? That's the way it is. Well, as you may have guessed, Excel has a tool that will generate this entire table of results directly. It's called the Descriptive Statistics tool, and it's on the Data tab under Analyze. Now, if you haven't used it before, you probably won't see it. It needs to be installed for first use. So if you go to File, down to Options, and go to Add-ins, so it's File, Options, Add-ins. At the bottom of the page you see Manage Excel Add-ins. Just click on Go and check off Analysis Toolpack. And you might as well check off Solver Add-in, because we'll use that in later lessons, and say OK. I'll say Cancel because I already have it installed. And here it is then on the Data tab, Analyze, Data Analysis. So in the Data Analysis dialog box, you want to find Descriptive Statistics, listed alphabetically, and say OK. So you want to input the range of data to be analyzed. Yeah, so click in the Input Data Range box and scroll over not only the 3 data points, but also include the title. And then make sure you check off Labels in the first row. That way Excel will label the data. Now, it doesn't really make much sense here because we only have one data set, but you'll see that in later tests that we use where we're comparing 2 or 3 data sets, it makes it much easier to keep track of what data belongs to what analyte. So we'll check that off, Labels in the first row. In Output Range, in this box, click your cursor in the cell that represents the top left corner of where the data will be displayed. Just make sure there's nothing below it that's going to be overwritten. Check Summary Statistics. Notice the confidence level by default is 95%. You don't have to check it. All you have to say is OK. And there it is, all the data that we generated. We have it immediately in front of us. So we have the mean, the standard error, the median, the mode. The mode is not available. Why not? Well, the mode is the most common number. Well, there's only one of each. Maybe that's why. Standard deviation, sample variance, kurtosis, skewness. We'll talk about those in a minute. And the rest is all here. So the question would arise, well, what would I report for my answer? Do I report 93.50333? How many decimal points do I report? So here's the rule. You're allowed to report 1 sig fig in your standard deviation because a standard deviation is an estimate. So you want to reduce this to 1 sig fig. That's 0.8. And therefore you can only report the same number of decimal places in your result as you have in your standard deviation. So the first sig fig in the standard deviation occurs in the second decimal point. So you'd have to report the mean to the second decimal point. 50. That's the rule. And you report your maximum and minimum to 2 decimal places as well. All right, what about this kurtosis and skewness? Recall on page 168, here's the calculation of skewness. It's a measure of the normality of a data set. Recall the absolute value of the skewness. When it is less than or equal to 2 times this standard error of the skewness, root 6 over n, then the data is deemed to be normal. Now here's the calculation, and very kindly Excel did that for us. Tells us the skewness is this value here, about 0.20. Let's calculate 2 times the standard error of the skewness. It's equal to 2 times root 6 over n equals 2 times square root of 6 divided by n was our number of samples, that's 3, close bracket, enter. So 2 times the standard error of the skewness is 2.8. And in our case, certainly then the skewness is way less, it's 0.2, and therefore Excel deems this data set to be normally distributed. What about kurtosis? Kurtosis is calculated with this daunting looking formula here, and when the absolute value of kurtosis is less than or equal to 2 times the root of 24 over n, that is the standard error of kurtosis, 2 times that, then the data is deemed to be normal. If we look at our result that it gave us, it says division by 0. Now, why is that? Well, in the denominator of both of these terms, we see there's n minus 3, and we had n equal to 3, so you can see that this would evaluate to 0 and to 0, and hence it couldn't be calculated. Which tells us then you could not calculate kurtosis for 1 sample, or 2 samples, or 3 samples, because you'd always have division by 0. It looks like you need at least 4 samples to calculate kurtosis. So that's it for margin of error. Page 181, F-test for sample variances. Most everyone appreciates that when a fair coin is randomly flipped, it has a 50-50 chance of landing heads up or tails up. But if a classroom of students each flipped a coin 10 times, do you think that each individual student would observe that their coin landed 5 times heads up and 5 times tails up? I think most everyone appreciates that only some students would obtain an exact 50-50 split of heads and tails. But if we tallied up the results of all the students in the class, we expect that the average of many tosses will closely approach a 50-50 split. You see, random results are only estimated with high precision when many replicates are performed, and only then does this give a good estimate of the population mean and precision. When just a few replicates are performed, the sample mean and precision are usually different than the population mean and the population precision. If you analyze a homogeneous sample in triplicate and then repeat this, the same analytical procedure being used in both cases, with only random variation occurring, do you think that the mean and the precision of the 2 sets of analysis will be exactly the same? Likely not. But if you repeat this many times, we would expect that the cumulative mean and average precision will each approach constant values. What if you want to compare 2 different methods for analyzing chloride and water? You could use the Moore titration method. You could use the ion selective electrodes method. If both tests were run in triplicate and 2 different averages and 2 different precisions were measured, how could you determine if these differences were the result of random variation of the 2 methods of equivalent accuracy and precision, or if the 2 methods actually gave statistically different results? Well, you could repeat these tests on the same sample many times, perhaps dozens or hundreds of times. If both methods had equivalent accuracy and precision that only differed by random variation, the 2 means would approach and the 2 precisions would approach each other, and eventually the mean and precision of one method would be indistinguishable from the mean and precision of the other method. Make sense? But what if you can't or don't want to perform dozens or hundreds of analyses? Is there a statistical test that we can apply to determine this? Well, good news. Yes, there is. The F-test is a statistical test for comparing the variances or precision of 2 data sets. And the T-test is a statistical test for comparing the means or averages of 2 data sets. We're going to start with the F-test for sample variances. Here's the calculation. F-stat A dimensionless value is simply the ratio of the variance of one method divided by the variance of the other method. And the only stipulation is that the variance of the first sample set must be greater than the variance of the second sample set. In this way, the f-stat will always be greater than or equal to 1. If by chance the two methods gave exactly the same variance, then the f-stat will be exactly 1.0. But if the variances differ, the f-stat will always be greater than 1, never less than 1, because we always put the larger number over the small number. Well, then the question arises, at what point will the f-stat be large enough to conclude that the variances are different? Well, when f-stat exceeds some critical value called f-critical, then we conclude that they differ. And the f-critical value is read from an f-table, and the value chosen depends upon two factors: the confidence level we choose and the number of degrees of freedom of both variances. Page 182. There's more theory we need to consider. Hypothesis testing and confidence levels. In chemistry, the 95% confidence level is usually chosen. For statistical tests, the null hypothesis H0 is assumed. This means we assume there is no difference. Null means nothing. The alternate hypothesis HA is that there is a statistical difference in the results. If the f-stat is less than or equal to f-critical, we accept the null hypothesis at the 95% confidence level and predict that for every 100 times these two methods of equal variances are compared, only 5 times out of 100 would f-stat turn out to be greater than f-critical. Only 5 times out of 100 would we incorrectly conclude that the variants are different, because only rarely would f-stat exceed f-critical when the variances are equal. This is called a type 1 error, or false positive. It means observing a difference that we reject H0 when the difference is not real, but due to chance. Using lower limits, like 90% confidence limit, would simply increase the chance of rejecting data varying due to chance. The F distribution, shown here, plots F critical values on the x-axis of this table. So the F distribution is actually a family of distributions, as you see, whereas the normal distribution and the t distribution are both symmetrical and centered around 0. They both have positive and negative values. You notice the F distribution only has positive values and is skewed to the right. As the degrees of freedom get very large, this F distribution becomes symmetrical and centered at an F value of 1. Here the gray curve represents that. And one-tailed versus two-tailed F-tests. So say, for example, your company refines canola oil, which has a strict upper limit of 0.1% water. Can't have water in the oil, would make it look turbid, people won't buy it. The approved procedure for measuring moisture or water is drying, and it's slow. However, you have found a rapid method using an NIR spectrometer. But you can only substitute the NIR method if you can statistically demonstrate at the 95% confidence level that its precision is at least as good as, not worse than, the established drying method. See, it's no problem if the NIR precision is better. That's not a problem, only if the precision is worse. In this case, a one-tailed F-test is used. This means that 5% of the area under the F distribution lies to the right, as you see here in the diagram on the left. So here 95% of the area lies to the left of our F critical value, 5% lies above. If, on the other hand, you want to determine if the precision of the NIR method is the same as the approved method, that is not greater than and not less than, then a two-tailed F-test is used. In a two-tailed F-test, shown above right, 95% of the area under the curve lies here, and the 5% is divided by 2, so we get 2.5% above and 2.5% below. A two-tailed F-test determines if the second method's variance is different, either higher or lower. Is it the same or different? Page 183. So how do we get F-critical values from F-tables? We locate the intersection of appropriate columns, the degrees of freedom of the numerator, dfn, and the appropriate row, the degrees of freedom of the denominator, dfd. Keep in mind that dfn is for the data set with the larger variances. For example, the F-critical value at the 95% confidence level, given dfn is 5 and dfd is 6. So dfn, degrees of freedom of the numerator, the sample set with the greater variance, and dfd with 6. The point of intersection is this group right here. So we need to find the appropriate confidence level. So for an alpha value of 0.05, which is 95% confidence level, F critical is 4.39, and that's for a one-tailed test, where all 5% is to the right of F critical. However, if you want a two-tailed test at the 95% confidence level, you look up 0.025. There's 2.5% on either side of the distribution, and F critical now is 5.99. Be careful. Page 185. Here's a problem for us to work on. The concentration of chloride ion in the Detroit River has varied over the last number of decades. Recent values are between 20 and 30 milligrams per liter. The same sample of river water was analyzed by ISE and the Moore method as shown below. Here's the data for the ISE, 7 samples. Here's the data for the Moore method, 6 samples. Determine the two-tailed probability at the 95% confidence level that these two methods yield essentially the same variance. That is, they differ only due to random error of the method or analyst, or if the methods actually yield different variances. We're going to work this out in an Excel spreadsheet, so we should go there now. Here's the Excel spreadsheet. It's labeled Excel Stats, and we're looking at the worksheet called F-Test. Let's fill in this table of values, and we'll determine if the variances of the two methods are the same or different. For the count, tab, scroll over the argument 7, and we can pull that across. So there's 6 samples for the Moore method, 7 for the ISE. The degrees of freedom will be equal to the count minus 1. For the mean, we use the average function. And we can drag that across. Standard deviation equals STDEV dot S tab. All 7 values. We drag that across. Now you may be wondering, we don't have a value in cell D10. What does Excel do? If there's no value in the cell, it just ignores it. So it'll give the same value as if you chose only the first 6 cells. So it's okay. For the variance, you could just square the standard deviation, but there's also a function for it called var dot S tab. We can drag that across. Anytime you report a standard deviation, you must also report the relative standard deviation. That's equal to the standard deviation divided by the average value times 100%. And 3.0 is not all that great. 1.5% RSD for the ISE is pretty good. The literature says you can get within 2% if you calibrate every half hour. On the ISE, that's a classical wet method, so we should be able to get less than 0.5%. So whoever did this was somewhat sloppy. In any case, so the Fstat is equal to the ratio of the variances. 0.531 for the Moore method divided by 0.170 for the ISE method, so 3.13. So are the variances the same statistically or different? We need to get a value from the table. Here we have 5 degrees of freedom in the numerator, 6 degrees of freedom in the denominator. We want the 0.25 alpha value, which is 5.99, is our F critical value at the 95% confidence level. So what's our conclusion? The F stat is less than F critical, so we accept the null hypothesis that the difference in variances is due to random variation rather than a statistical difference in the precision of the two methods. Excel has a function built in for comparing two samples for variances. We'll find it on the Data tab under Data Analysis, and it'll be ftest 2sample for variances. Just say OK. You want to give the data range that it's going to test. Variable range 1 will be the data with the higher variance. That'll be the Moore method. Include the title along with it so that it's labeled when we see it. Variable range 2 will be the data set with a lower variance. Make sure you check off labels and make sure you set alpha to 0.25. 0.5 is default, but we want 0.25. The reason is we're doing a two-tailed test, so we need to split our alpha value in two. For the output range, click in the cell here and select the cell that is in the top left corner of the range where it will display. Just make sure there's nothing below it and say OK. It's telling me it's going to overwrite existing data, and that's OK. So here's the data we're given by Excel. Too many sig figs here. So we have our means, we have our variances, and we have number of observations and degrees of freedom. And here we have the F-stat value and F critical as we determined from the table, 5.99. So the conclusion is the same. There's no difference in variance at the 95% confidence level. Notice that Excel also displays a p-value, and this is the probability that the difference in variance is due to random error. So a p-value of 0.1 corresponds to a 10% probability. But you must always double this value for a two-sided test, since only the upper half of the probability is considered. Recall in our two-tailed F-test diagram, we're only considering half the area, the upper half, and so 10% is here, another 10% is on the low side. So the probability is actually 20% that the difference between the two methods is actually due to random error. So we can't reject the null hypothesis. The only time you reject the null hypothesis is when the probability is less than alpha. That is, if p is less than 0.05. So you retain the null hypothesis when the probability is greater than alpha. You reject the null hypothesis when the probability is less than alpha. As mentioned earlier, Excel contains a function that will give us the upper F critical value. Equals f.inv. There it is, tab RT. Now our probability is 0.025. Because we're using a two-tailed test at the 95% confidence level, we cut the significance level in half. Instead of writing 0.5, we write 0.25. Degrees of freedom, you must put the degrees of freedom for the larger variance first. That was 5 and a comma. 6 degrees of freedom for the lower variance, close bracket, 5.99, the same as we got above. Excel also has a function that directly gives us the probability that the variances are the same. It's equal to f.test, and we enter the arrays of the two data sets. In this particular case, it doesn't really matter which array we put in first. It works in either case. So here's one array of samples. We don't include the labels this time. And here's the second array of samples. Close bracket. So our probability is in fact 20% that the differences in the variances of these two methods is only due to random chance, random variation, at the 95% confidence level. This is the same probability level that we determined from the descriptive statistics tool, but we had to remember to double it in this case. Using the f-test, it gives us the probability directly. Again, when the probability is greater than the alpha value of 0.05, we must accept the null hypothesis and say that the differences in the variances is due to random chance. So that's it for this lesson. In our next lesson, we will look at tests for comparing sample means.